Okey-dokey. So we're into, let's see, basically the last topic that we'll talk about this semester. I imagine that just given we've got, what, 5 essentially class periods left, we'll probably just spend a couple of those, talk about some of the basics of organic chemistry, and then we'll see if we can find a day or two or a class or two just to kind of, I hate to use the word review, but I guess just at least talk about what we've gone through over the whole semester there, just to kind of jog the memory a bit too. Yeah, what's up?
We really have 4, and we don't have classes on Friday.
Oh, is it not the Friday there either? Oh, okay. Then yeah, whatever we'll have left, we'll adjust as it is. But yeah, thanks for reminding me of that. I guess I forgot about that too. All right, I'm gonna have to teach really fast now and do it. But it's all good. All right. So what we want to do at least with organic chemistry is just kind of skim the basics of it is what it is. And as I mentioned last time, we'll be taking, I would say, a fairly sharp turn from what we've been doing for the rest of the semester. You know, a lot of the stuff that comes through in the second semester of Gen Chem is, math based. Like, oh, here's a concept, and here are the equations to describe this process or this reaction and these kind of things. But there's not going to be any, let's say, equations that we learn in organic chemistry. And I'm not just talking about here, even for you guys who are going on to the full organic course next year. There's not going to be any equations that we have to learn from that. Although there is going to be math, right? So, but don't worry, we'll talk about the math here in just a second, and or as soon as we get to it. So we'll learn a couple of the basics. What we will be doing is looking at how to draw organic molecules and how to identify organic molecules. Is kind of the basics of what we'll be getting in there. This is chapter 24. Yeah, chapter 24 in the book there. I think that's, gosh, I just looked it up before I came down here, now I forgot. It's a chapter that's about the chemistry of life is what they call it, and that's organic and biochemistry is what it is. I'll post the chapter for you guys in case I'm wrong with that. But that's where we'll be kind of going through the opening part of that and adding a little bit to it. The other thing I just needed to mention is as I walked down in here, I also realized I forgot to put the quiz up for you guys as I promised today. Whoops. I know you guys are sad, I can tell, right? But okay, I'll open something up and we'll give you guys a little bit extra time to kind of get that planned in there since this was me being dumb here. Let's see. Do you guys want the quiz on Fridays? Would that be okay for you guys? You guys actually said yes. I'd say no, and just like every day I throw out, you guys are like, no, that's not going to work either. That doesn't fit my schedule, right? Right, then we'll do it for Friday, and I'll actually not forget it this time, right? Okay, well, and that'll be again. So this is just going to be on the electrochemistry chapter there, right? So not on the organic stuff. So sorry about that. I don't mean to cause confusion with you guys. It's just I'm an absent-minded professor some days. What can I say? So okay. I think that's all I needed to chat with you guys about with that. Yeah. So we'll get started with prayer then, and then we'll start to unravel the world around us with organic chemistry. But Lord, we just thank you. We just thank you yet again that we can just whenever we want and whenever you put on our hearts and whenever we feel in our hearts, Lord, we can just turn to you just for a conversation or just for some time to spend with you in our hearts. And we just thank you for that gift, Lord. We thank you that we can do this whenever and wherever we are. And we just pray that we don't lose that desire for this, Lord. In fact, we pray that you grow it in our hearts, Lord. You grow in our hearts to be something that we crave and desire and need every day. And so we just pray that, just to increase our faith, Lord. Just help us to use the gifts and the talents that you've given us, Lord. Help us to use the resources and be good stewards of everything that we have, just for your kingdom and for your sake, Lord. We just pray to be good and faithful servants today, and we pray that you just speak clearly into our hearts as to what it is that we can do to serve you, Lord. We just pray this in your name. Amen. All right. Cool. All right, so organic chemistry. Now, organic chemistry, broadly speaking, falls into, let's say, one of the 5 topics our main areas of chemistry. We have organic chemistry and inorganic chemistry and analytical chemistry. We have physical chemistry. We have biochemistry, and there's a couple other topics that are kind of broken down like this. It's not meant to be a completely, let's say, discriminatory break of what chemistry is. It's just there's some broad topics that we talk about. And if we had a chemistry major, right, we would have courses that kind of fall into all these different categories, right? We'd have an analytical course in physical chemistry and inorganic and all these kind of things, right? So some of them we do have, right? PChem is one of these things that if you guys are biochem majors, we might end up taking here, right?
P-Chem?
Physical chemistry, yeah. Sorry, yeah. Going with the lingo, right? Right? And then obviously, you guys will be taking, or not all of you, right, but some of you guys will be taking OChem and organic chemistry, and then, along the way, we'll teach a little bit bits and pieces of some of the other things here. So it just depends on, what major you're doing and kind of the designation and these kind of things. For instance, we're trying to bring in the BS in biochemistry, and that would add in some of these courses along with it, is what it is, right? So, like I said, just kind of, it depends on what your desires are and what major you guys are doing, right? But organic chemistry is one of these things where typically you end up taking 2 semesters of this as an undergraduate, right? And then you end up taking this again when you go to graduate school, right? And so there's decades and decades and years of learning to be done, right? It's this topic that's ever expanding. It's one of these active areas of research. It's one of these places that, a lot of the, let's say, the compounds and materials and the pharmaceuticals and whatever you guys might say, is derived from, in some way, organic chemistry, right? So there's a big chunk of this, what I'm saying is that it focuses on the reactions of carbon, right? And so the first thing we gotta do before we can make all these fun things is we gotta figure out, well, what in the world does carbon do and how does it behave, right? So that's kind of the intro part that we're going to talk about here, right? Just looking at some of the basics of how carbon acts. Okay, so now we really knocked the rust off here. I got some work for you guys. So what I want you to do so draw me the Lewis structures for something which you guys have never drawn before, okay?
Methane?
Oh yeah. Remember how to do Lewis structures, right? You guys are like, oh, let's see, well, there's a couple of steps that we usually have to take along the way, right? I think maybe for something like methane, you guys probably did this all in the brain there, right? Probably have to count valence electrons, to count total electrons, to draw a skeletal structure, we have to draw things together, right? Connect things together. There's a certain number of steps to get there. Right? You guys remember those steps?
Yes.
One person does, everyone else is like, yeah. We'll test it here in a minute, right? So if I draw methane, right, this is what I would come up with, right? We'd have a carbon in the middle, right? Have a couple hydrogens on the outside. That looks nice, right? Remember when we are drawing our Lewis structures, we don't have to worry yet about the 3-dimensional structure of this, right? We'll come back and we'll clarify that in a little bit also, right? So there we go, there's our Lewis structure for methane, fantastic, okay. Another tricky one, there's carbon dioxide. While you guys are at it, I want you guys to do carbonate, okay? think I'll just stop torturing you guys with those four there, and then we'll ask you guys an important question.
Carbon is 4, oxygen is 6, okay, right.
You copying off her words? No, just. Don't have it memorized anymore, huh?
Is CO2 polar?
CO2 polar? Good question, isn't it?
Cause like, apparently my brain is too sleepy to function. And either I'm really bad at math, or I cannot make this balance.
So we're gonna have to remember our steps on how to draw Lewis structures, right? So I'll walk you guys through in a second.
Oh, hold on. Okay, I'm just bad at math.
Okay. Yep. You got it.
For some reason, I thought that 12 plus 4 equaled 18, so I was trying to figure out.
Yeah, not on Wednesdays.
No, on Wednesdays we wear pink.
Cool. All right. So we have 4 compounds, which is a minuscule subset of the billions and trillions of carbon-containing compounds that we could sit down and try and draw through. But one of the things, or one of the skills that you're going to have to start to develop in when you go through organic chemistry is really start to look at the patterns of things, right? So, what do we start to notice about these sets of compounds here? Yep.
Carbon is always in the center.
Okay, that's something that we see for this particular set here, right? Which brings a good question. How do we know what goes into the middle of a Lewis structure? How do we assess that? Yep.
The least electronegative?
Typically, it's the least electronegative, right? So when we're going through and drawing some of these molecules, we have to remember what electronegativity is and how that's going to influence our Lewis structure, right? So that's one thing to notice. What else? What?
Carbon likes double and triple bonds.
That may be true. That might be true. Let's say I don't know if we could say that it likes it. I would say something a little bit more general in saying that it can make single, double, and triple bonds, right?
Carbon will only have a single bond with hydrogen.
Aha, right? So carbon will only ever have a single bond with hydrogen.
But that's more
Right.
because hydrogen can only have a single.
That's correct, right? But if we remember, hydrogen is one of these, let's say, exceptions to our octet rule, right? Hydrogen's always gonna be on the periphery of molecules where it'll only ever have one bond to it, right? So if you guys ever draw more than one bond to a hydrogen, it's gonna be incorrect, so don't do that, right? What else?
If there's more than one carbon, it's probably gonna bond to another carbon.
Okay, right, so carbon can make bonds with itself, right, and make, let's say, longer chains of molecules, and we'll definitely see that as we go through. What else? Something very important. You guys are all seeing. What's up?
Pyramidal geometry will lead to polarity.
That's not necessarily the case, right? Or broadly speaking, certain geometries can be polar, right? Any geometry could be polar, right? In this case, we might, like within this small subset, we could say that. Martin,
It only makes bonds with like other non-metals.
what do you mean?
Like other, like oxygen and hydrogen are non-metals.
Okay, so we have to, so we could start to take a look at what specific bonds carbon likes to make with different atoms, and that is going to be something important to pay attention to. Right? What else?
This is gonna be something super obvious that we're all like, oh, when you say it.
Yeah.
Is it something that's probably so obvious we're overlooking it?
Yeah. I'm not saying everything you guys have said is incorrect, right?
It's just you're looking for a very specific.
No,
trait.
I'm just looking to see what you guys are observing first, right? If I just wanted to give you guys answers, then I'd just sit here and rattle off a bunch of bullet points, right?
Carbon is present in all of them, but we've already established.
You got
that.
it, all right, everyone, all right, put that in your notes.
Oh, it never has valence electrons, maybe?
Aha, right, so that is something that's interesting to note, right? We're not gonna typically see lone pairs on carbons, right? We're not gonna typically see lone pairs on carbons. That would be outside of the norm. Now granted, we've got a small subset here, right? So it'd be really tough to make that definitive statement, right? But we do notice that at least in the subset that we have, carbon doesn't have any lone pairs, and in fact, that is gonna hold true for all the molecules that we do end up talking about for this, let's say, section.
You're still looking for something else?
Yep.
Yeah.
There's a couple other important things. You guys are getting frustrated. You don't have to get frustrated by this, right? It's just
No, because I hate when I know that there's something obvious that I'm missing.
yeah.
I know it's gonna be one of those things where I'm gonna be like beating myself up all day if I don't get
That's
it.
all my job is. My job is to frustrate you guys, to make you feel bad, right? Some of you guys are smiling, so you're like, yeah, Dr. H, it's working. How many bonds does carbon have in the top compound?
4.
How
It
many does
can't
it
have
have?
more than 4
How many does
bonds.
it have in the second?
4.
How many does it have in the third? How
It
many
always
does it have
has
in
4.
Okay. Now, you guys already knew that,
Right?
didn't you?
Yeah.
Because how do we know, or how can we predict how many bonds any atom typically has?
The number of valence electrons, and since carbon has 4, then it either has to have 4 bonds or lone pairs, and we've already established it doesn't have lone pairs.
Correct, right? So remember, we can take a look at the periodic table and make an assessment about how many bonds something's going to make, especially the atoms of carbon, nitrogen, oxygen, and fluorine, okay? So carbon, nitrogen, oxygen, and fluorine are going to be very useful compounds, right? Excuse me, very useful atoms. We're gonna see them quite a bit as we go through a broader discussion of organic chemistry. Now, do you guys happen to remember why carbon, nitrogen, oxygen, and fluorine are kind of special, as I call them out?
They're the most electronegative?
No. Fluorine is, oxygen and nitrogen are, but carbon's not all that electronegative. But what makes them particularly special in conjunction to drawing Lewis structures? Yes, they do. In fact, there's let's say, a rule that they follow.
The octet rule.
There it is, right? So carbon, nitrogen, oxygen, and fluorine exclusively follow the octet rule, okay? Which is always funny to me, right? Because we call this a rule, and then really it's only those 4 atoms that end up following it, right? Every other atom on the periodic table can violate the octet rule. I'm not saying it always will, I'm just saying there's carbon, nitrogen, oxygen, and fluorine will exclusively follow the octet rule. So if you go outside of the octet rule for any of those, then you're doing something wrong, right? But remember, we're dealing with organic chemistry, and that's the chemistry of carbon, so very particular when you guys are looking at these carbon-containing compounds. Make sure you're following the octet rule unless there's some really good reason as to why you're not, right? And the book talks about that in a couple sections, which we'll briefly mention when we get there, okay? I'm not saying carbon can't disobey the octet rule. I'm just saying there has to be a special reason for it too, okay? So, carbon, when it's in its happy state, right? When it's in its, let's say, neutral, right, formal charge, a 0 formal charge, it's gonna have 4 bonds to it. And that's gonna be one of these important key bits to remember as we draw some of the more complex structures that we're gonna look at, okay? Carbon wants to have 4 bonds. Now, as you guys mentioned, we see that we can make single bonds, we can make double bonds, and we can make triple bonds, okay? So we have to have just some combination of single, double, or triple bonds that adds up to be 4 for every carbon in there, okay? Something else important that you guys pointed out. Hydrogen only ever has 1 bond to it, okay? Now, carbon's best friend in the world of organic chemistry is going to be hydrogen, okay? Now, you guys already knew this too, right? No, I never thought of it. Have you guys ever heard of the term hydrocarbons?
Yep.
Right? What do you think a hydrocarbon is?
Anything where hydrogen is bonded to carbon.
No, it's anything where carbon and hydrogen are present in the molecule there, right? So what we're going to learn to draw first are all these different hydrocarbons, is what it comes down to. Okay? And we're going to use the rules that you guys thought up here to kind of, let's say, develop some shortcuts on how to draw these things. Okay? So keeping in mind the number of bonds that we want to make, right? That carbon and hydrogen are good friends with each other, right? These kind of things. Right? We're going to start to develop, let's say, a shortcut for how we can draw molecules.
You mean the thing with the corners representing?
Yeah. But before we get to that, let's see here. So to step outside of the realm of organic chem, well, no, we can stay in the world of organic chemistry a little bit. CH2O, okay? So let's quickly walk through how to draw a Lewis structure for molecules again, right? Remember, there's 4 steps when you guys are drawing a Lewis structure, okay? So step number 1.
Count valence electrons.
Count electrons, right? So what we need to do, and when you guys are going through and drawing Lewis structures and all these things, right? We have to make sure that we have our periodic table in front of us, right? Because that's where we're going to get our valence electrons from. Right?
We have ephemeral.
Okay, that's fine. Do you guys remember how to get valence electrons from the periodic table? Yes, everybody? I mean, it's okay to say no, and I'll go over it, right? It's like I don't need to waste your guys' time when I ask you, right? Okay. So how many valence electrons does carbon have? 4, right? Each hydrogen has 1, right? So we got 2 from there. We got 6 from our oxygen, right? Fantastic. So we have a total of 12 electrons to work with, yes? Yes. Okay. Step 2. Skeletal structure. Okay. So skeletal structure is where we build the basic shape of what we're going to draw here, okay? And this is the other thing that you guys were mentioning when we went through our list of observations there, right? We typically start by putting the least electronegative atom into the middle, okay? Do you guys remember how to identify electronegativity? Alright? Fluorine's the most electronegative, and then as you move away from it in a diagonal, it becomes less electronegative, right? Mhm. So carbon's in the middle. Our skeletal structure then says surround, right, the central atom with the other atoms and connect everything. I'm just going to change colors here. Connect everything with single bonds, right? Good. So a couple of quick things to remember. My bonds in red there that I drew, what do we call those?
Single bond?
Mhm. What else are they called?
I know there's a special term, but I don't remember.
Hmm?
Those sigma bonds.
Those are sigma bonds also, right? So single or sigma bonds, when you guys talk about this, are the same thing. Sigma bonds are always the first set of bonds to get created between any atom ever, okay? So in the book, when they talk a little about hybridization and sigma and pi and all this kind of stuff, a sigma bond is just a single bond, okay? Now, of course, there's a slight modification of this, but again, it's a little bit outside of what I want to talk about at the moment, right? For the moment, we can just take sigma bonds, single bonds, that kind of thing. So if I ask you as a question like, hey, how many sigma bonds are in this? You guys would count 3 of them. Got it? Good. So there's our skeletal structure. To do our skeletal structure, we have to use 6 electrons. Everybody with me on that one still? Okay. So now we have to fill in the remaining 12 electrons. So
No.
instead, excuse me, 6 electrons, right, to get the 12. So fill in remaining electrons. And how do we do that?
Electronegativity.
So we got 6 electrons that we need to fill in here. Again, we go and turn to our periodic table and say, where's our most electronegative atom? And we start by filling in valence electrons there. Got it? So oxygen is the most electronegative here, as it tends to be in most molecules. So we put the remaining 6 around there. And we're done, right?
Well, aren't we gonna make it geometric?
We'll get to that in just a second, right? Are we done?
Carbon can take another bond.
Aha. Did we draw a Lewis structure though?
Right.
The answer is yes, we did. Did we violate any, assuming I didn't make any mistakes, did we violate any of the 3 rules along the way? No. But how many steps did I say there were? 4. The 4th is the most important step you guys will ever do for every class of chemistry that you guys ever take. In fact, for every class that you guys ever take.
Make sure carbon follows the opposite.
That's right. When you guys are in philosophy, right, and you guys are done writing your essay, step 4 should be make sure carbon has. All right, you guys with me on this? Very philosophical. What's the 4th most important step always do? Check, right? There's got to be a series of, let's say, tests due to make sure we drew the right molecule or that our answer is correct or these kind of things. Right? Now, I'm going to skip some of those because my assumption is that you guys still have your notes or you remember at least part of this from last semester when you guys learned it. But there's one very important step, all right? One very important test that you guys need to remember how to do. Those are our formal charges. Do you guys remember those?
Yep,
Do you guys remember how to do those?
yep.
Okay, one person feels confident. So give me the formal charges for what we have drawn. See what you guys come up with. See what you guys remember. for what I have drawn.
Oh, for what's up
Yeah.
there.
I'm not saying you're not wrong with that, but for what we have drawn at the moment. So oxygen has a formal charge of 7, is that what we're saying? Where'd you get that from?
I counted up there's the electrons there, and
Mm-hmm.
then in my circle.
Mm-hmm. And we gotta subtract something from the stuff in the circle. So valence minus the circle. Oh, no, it's,
I don't know.
oh, yeah. Somebody got a spare pen or pencil? Oh, no, you failed me as a student, Mark. Oh, man. Okay, well, you guys don't remember everything that I tell you? Close. Almost there. You got the right idea, just a little bit off with a couple of your numbers here. That's okay. Oh, you're looking back. Okay, that's fine. Okay, we will go through it.
And this is like 4 years ago?
4 years ago, oh, okay. So really knocking the rust off there, I got you. Cool. Alright. So remember, there's a couple different ways of doing formal charging, what it is, right? There's a formula where you guys can, add bonding electrons plus lone pairs and divide by, I forget that formula, right? That's why I don't use it, because I don't have a memory for these kind of things. Okay? But if you guys do recall, what I do, right, is I do my magic science circle, right?
Magic science circle.
Right, and my magic science circle surrounds the atom that I'm looking at, and it cuts through the bonds of the structure that I've drawn. Okay, everybody with me still? And then what I do is I count how many electrons are in my circle. So 1, 2, 3, 4, 5, 6. Okay, those are the easy ones. I just count my lone pairs. And then since I cut my bond in half, right, I count 1 electron from my bonds. Good? So I have 7. I have 7 electrons in my magic science circle, and I start out with 6 valence electrons. Okay? So valence electrons minus my science circle will get you your formal charge. Good? So what's the formal charge for oxygen?
Negative.
-1. Right? We could repeat this for everything. Right, there's my carbon, I count 1, 2, 3 from the bonds. Science circle, right? Valence electrons minus. So carbon would have a +1. That's all there is to it. Okay? Not too bad, right? Sorry. Good. Now, what do we remember about formal charges, though? A couple of quick things to jog the memory. What do you guys remember about formal charges? Yep.
The most electronegative atom has to have the lowest formal charge.
So let me back up a little bit on your statement there. When we have to put a formal charge on something, right? If we have to put a formal charge on something, we want our electronegative atoms to have the most negative formal charge, right? I've got a -1 on my oxygen and a +1 on my carbon. That adds up to be 0, okay? The sum of my formal charges has to equal the overall molecular charge, right?
Right.
So if you guys go back and take a look, we did CO3 2-. right, is one of our first set of compounds there. That 2 minus, right, we could go through and assign the formal charge for everything, right, and that would be the sum of our formal charges there also. You guys remember that? Yes? Okay. Okay. Now, the rule of thumb, so to speak, right, is that, oh, what's up?
Sorry, don't interrupt.
No, go ahead, what's up?
Can you go through the Form M3 again? I didn't catch that one.
Oh, yes, so I'm looking at carbon, right? I cut the 3 bonds that are around there, and I count 1 electron for each bond, is what it is, right? And then I start out with 4 valence electrons for the carbon.
Oh,
So 4 minus 3 is plus 1. Right, that's all it is. Now the rule of thumb for formal charges is we want to minimize them, okay? That is, we want to try and get everything to 0 if we can. And just to keep things a little bit simple over here. So there's just the same molecule that has a minus. Be explicit, that has a -1, this has a +1. Okay? So by assessing our formal charge, we say, hey, there's something unusual. Okay? Now there should be something else unusual that should immediately pop out to you guys also, based off of what we started out this class talking about. What do we notice about the carbon in the structure we have drawn?
It only has 3 bonds.
We only have 3 bonds to it, right? So we have to give it another bond, but we can't add electrons to it. Right, so what we're going to do is give a double bond there from the oxygen, okay, to the carbon. Good?
Mhm.
What happens to our formal charges when we take a lone pair into a double bond?
Goes to 0 in this case.
Our oxygen is going to have a 0 formal charge. Our carbon has a 0 formal charge. Everything's obeying the octet rule, right? So what does that mean?
We're done.
We have a nice, happy molecule, right?
Hey.
Good?
Yep. What's it called?
This is formaldehyde.
Interesting.
Yep.
So what makes it do the thing?
The thing?
Yeah, like, okay, it's like one of the best preservatives, right? Like,
Yeah.
From decay. So how does such a simple structure have that property?
Good question, right? I don't know if I have a great answer for it. It's something I have to look up, to be honest. It's it reacts quite readily with a lot of, let's say, amines and amino acids. So it might have something to do where it prevents like oxidative decay or something like that. That could be what it is. I'd have to go look it up, to be honest. I don't know the exact prevention mechanism, right? But formaldehyde, aside from it being used to preserve things, it's used a lot in like to form plastics and things like that also, right? It's in pretty much everything that we, every kind of plastic that we use these days, right? So very, very common molecule.
Isn't it a carcinogen as well?
Yes, yeah. Cool.
Why carcinogen though?
Probably for the same reason that it preserves things, right? So some kind of reactivity with biological species, right? Can't grow cancer if you're dead, right? So that's probably what it comes down to. Good, so we remember a little bit about Lewis structures, right? Remember a little about formal charges and these kind of things, right? And I lied to you guys already, do you guys see that? I told you there wouldn't be formulas, and what did I tell you? You guys had to subtract numbers here already. I'm sorry. I know, 6 minus 7. Yeah.
Worst teacher ever, I'm writing a bad review.
That's okay. You gotta be known for something. Okay, so let's, you guys already did methane for me, right? So there's that, you don't have to go through that again. Let's up the ante a bit here. Okay. Keep it a little bit simple at the beginning there, so C2H6. most energy come from her though?
The what?
F minus.
The what?
We'll talk about
It has, the,
it. Oh, you're saying I'm wrong, I'm sorry.
what did I miss?
Don't worry about it, we'll talk about it. It's fine, it's a good structure.
You said I missed something.
You did.
So what did I miss?
Don't worry, we'll talk about it. It's like you think I have a 30-second answer for you for all your questions. I don't. Okay, that's good. Two carbons. Yep. Otherwise you're making a porcupine there. Good, good. Excellent. All right. Looks like most of you guys are on the right track here. Okay. Carbon, carbon. Okay. Not too bad, right? We drew something. Always go back and double check. Each carbon should only have 4 bonds to it. Right? Each hydrogen should only have 1 bond to it. Right? And we notice that the carbons are the ones that are bound to each other. Right? Let's do something drastically different. You ready?
Uh-oh.
Okay.
What?
Now, question. How is this going to be different than what you guys just did?
Is it gonna be a ring? Doesn't it take 6 carbons for a ring? Can you make a carbon ring with 5?
Any other questions we have? You're about to use up your limit for the day here. How is C5H12 going to be different than C2H6? The answer is, it's not. It's just going to take longer to draw, right? Because instead of 2 carbons, what do we have?
5?
5.
But are they gonna ring?
Good question, right? So we can put 5 carbons, right?
Uh-huh.
We put them in a chain. And then we surround each of those carbons with the appropriate number of hydrogens, right, to fill in to get 4 bonds. Right? Is that what you guys did? Did any of you guys sit there and count up the Lewis structures, or excuse me, the valence electrons and do the skeletal structure? You guys didn't. I just told you to do it. What's wrong with you guys? Man, don't even listen to me 30 seconds later. So what are you guys doing? You guys are taking a shortcut, right? Is it a fair shortcut to take?
Hopefully.
Yeah, right? Why can't we take the shortcut of just saying, okay, we can put our 5 carbons in a chain, right? We can come back and fill in hydrogens to make sure that every carbon has, right, 4 bonds. 4 bonds to it, right? Why can we do that? Well, remember our rules that we started off with when we began our observations. You guys told me that carbon typically has 4 bonds to it. And you guys also told me that what? Hydrogen only ever has 1 bond to it. And then I told you the last bit of important information, which is hydrogen and carbon are best friends. Got it? So using those 3 bits of information is how we can shorthand our way to drawing this molecule without having to count valence electrons and figure out the carbons and all these kind of things. Got it?
Mm-hmm.
Good. Okay, I'm gonna ask you guys another question. You ready? I want you guys to draw this for me. So draw for me C5H12. Okay?
That's the one you just gave us.
It is. Man, do I hate making mistakes. So draw C5H12.
Using the full process.
No.
It's like the exam where you ask number 8 and then number 8 and then number 8.
2 number 10s, 3 number 10s. Wait,
Yeah.
haven't we already done number 10?
I was like, I need help on number 10. And I'm like, yeah,
Yeah,
I just decide which one.
Yeah, just point at this one. Right? What's one of the assumptions that we made in our 3 shortcut steps there?
That the bonds will take up all the valence electrons.
No, that's a truth, right? You know, that'll always happen.
That is a chain.
Aha! Right?
So it is gonna be a ring.
One of the assumptions that we made is that it's carbon, 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 right? That only one carbon is bound to the next carbon next to it, right? So we have carbon bound to a carbon bound to a carbon, right? Can you guys think about a different way that the carbons might be joined together? That's still, right? That's still,
It's okay, I'm just, oh no.
it still holds the C5H12. Give you guys a hint. It's not going to be a ring in this case, okay? And we'll talk about why in just a second.
Cause there's not 6?
No, that's not why. See what you guys come up with.
Well, we just started trying shapes and whole things.
Is it gonna be several dimensions? Like,
What do you mean?
Is it gonna?
Good. Can you
Oh.
think of another one? And they're like, no, that's it, Dr. H. 2 is my limit. I'm sorry, what do you mean by dimensions?
No, cause you know how like, sometimes you draw these if you're coming out of.
So we'll get to that point in just a second, right? So that's a good thing we haven't talked about that yet, but that's not what I'm drawing your guys' attention to here yet, right? Mm-hmm.
Just tell me, but when do you use this kind, there's
Mm-hmm. Yeah. The answer is always.
all of
Yeah, but it's one of these things where I'm building you guys up to kind of look at those kind of things, right? So you're not wrong with that, but what you're gonna do here is gonna be the same as what you have there, right? But we'll start to talk about that in just a little bit. So interesting thought here, right? So hang on to that idea.
It's not for you, but
Yeah.
Don't forget to fill in your hydrogens, right?
Well, yeah, but am I on the right track with like shape?
You guys, it's gonna be, guys, you guys ready for this?
What the heck?
Right? You guys are like, well, I don't know if that's right or not. Well, fill in your hydrogens, right? Take what I do there, fill in your hydrogens, and see if we get the 12. Okay? Still at 12 hydrogens with that one? Good. Okay. You guys want another one to practice with? Okay. One more to practice with? So just for argument's sake. So see if you you guys can draw me C5H12.
Okay.
Okay? Now look, take a peek at what we did between the first one and the second one. Okay? And what do you think we can do for the third one there? What did we end up doing? Okay? So we ended up taking, let's say, one of the CH3 groups at the end, and we moved it back to another carbon, right? So see if you guys can come up with something similar here, but be careful. That's all here. Alright, so that's that one. Don't give me that. So take a look,
It
right?
works.
It does it though. So take a look. Carbon to one carbon to one carbon to one carbon to one carbon. So this is the same as what we started out with, right? Carbon to one carbon to one carbon. All you did was just drew the carbon pointing in a different direction.
Yeah.
I like, now, we'll talk about what's going on with that, right? But take a look at it. So take a look at what we did with the carbons in
Yeah.
blue, right? Instead of having just one bond to another carbon, now we have one with 3 bonds to carbon,
Okay,
right?
what if you bring another one that's not doing, it's just doing things?
So,
Take another
so you have
of
this
those
one here,
ones.
right?
Yeah,
So what if you take that one instead of,
and then,
take this and put it there instead? What do you come up with?
oh, okay.
Do these things have different names?
Yes.
What are the names for each of them?
That one was 2,2-dimethylpropione.
And the straight one?
The first one we did?
Yeah.
That's just pentane.
Pentane? Oh, yeah, that makes sense. And, the third one with just the one, should we have?
2-methylbutane. Good. Now, some of you guys drew some other answers in there. And I like the way you guys are thinking. But some of what you guys drew are things called isomers, right? Or rotational isomers, or conformers. And we'll talk a little bit about what that is, because we're forgetting something, right? You guys are forgetting something important. That's okay. When we draw a Lewis structure, we make a couple of assumptions, right? One of the assumptions we make is that we draw everything flat. Are these molecules flat? No, they're not, right? And we'll talk about how that affects and comes up with some of the different structures that you guys drew there, okay? Now, what's the relationship between C5H12, C5H12, C5H12? Those are called constitutional isomers. So they have the same formula, but they're connected together differently. Got it? Do you guys see where the different connections are? The different connections are what? At the top there, we have this linear chain, right? One carbon is bound to another carbon, right? It's bound to another, it's bound to another, right? Here we've got a carbon with 3 other carbons around it, right? Here we've got a carbon with 4 other carbons around it, right? So we have these different types of carbons that are in there, okay? So there's a issue that we would have to deal with. I'm just going to mention it for you guys, but we're not really going to go too far in depth with this, right? When we're dealing with these different isomers and stuff, we have to come up with a name to separate these, 3 different compounds here. Otherwise, if you just give you a formula, any of those could be correct, right? So we'd have to have some way of indicating which specific compound I want you guys to work with. And that's where the systematic naming comes in with organic chemistry. Okay? Yep. Right? So if you remember way back when you first learned how to name your ionic and covalent compounds, I told you guys that there's two broad naming systems. One was the inorganic naming, which is what we did, right? And then I said, hey, there's another naming system which is organic, and you'll learn that later. Okay? So guess what time it is now?
Later?
Later, but not really later yet. We'll talk about that in depth in the first couple of weeks of the organic chemistry course, okay? But I'll give you a brief introduction on Friday there, just kind of how to differentiate between different isomers. The last point I'll make for today is that what we have here, these are all hydrocarbons, but these are specific hydrocarbons known as alkanes. Alkanes is what they are called. Okay? And the definition of an alkane is that we only see carbon-carbon single bonds. Okay, only see carbon-carbon single bonds. So I'll give you a hint about where we're going with some of these other things also. Good? Alrighty. So I will open that quiz for you guys there on Friday. And I will see you there, and we'll continue to talk about some organic chemistry.